So, let's try a few together then. I won't actually have you calculating these slopes anymore, but I just want to see how we do with a few examples here. So, just try the process. That's what I want you to get familiar with. See if you can figure out the implicit derivatives for those three examples. Okay, so I'll just do the first one. I'll give you a bit more time. So, let's see here. So, I'll just zoom in a little bit, make sure I have enough room here.
So, would you see how this one doesn't have a dx in it? This one goes to the other side there?
Okay, so for the first example, I would do this. It's going to be product rule for both, but you just got to remember that y has an extra piece to it. So this would be 2x times y plus x squared times dy dx. So that's the derivative for this first product here. Then for the second product, it would be 2y dy dx plus, sorry, I forgot an x there, times x plus y squared times 1. And that'll be equal to 0. Okay, so from here, I'm just going to move all my dy dx's, keep them on one side, factor them out. So dy dx, and the pieces that are left, here they are. So that'll be x squared plus 2xy. And on the other side of this, I'll have negative y squared, the other two pieces, which are these two. So negative y squared, take away 2xy. So that means the derivative of y with respect to x is negative y squared minus 2xy all over x squared plus 2xy. Okay. Now, for the second piece, maybe I'll do the second one and then I'll give you a minute to catch up. The second piece is going to be chain rule. So you have to be careful about the way you think of this when you do chain rule. So it's still going to be as we thought. It's going to be 2 times x plus y to the 1. But now I have to take the derivative of the inside. So the derivative of the inside piece is 1 plus dy by dx. Okay, so this is what I end up with for the chain rule on this example. Which, if I was to expand this out, I'd have 2x plus y plus 2x plus y dy by dx equals to 0. And now if I shuffle things around and try to solve this, let's see here. So it would be negative 2x plus y when I move that piece over. And then when I divide it, it'd be negative 1. So that's a strange looking, you might ask yourself, how did that happen? I mean, how does it end up to be just negative 1? Well, let's take a look at the picture and see what the graph would say. So x plus y squared has to be equal to 2. Is that the correct equation?
Yep.
Okay, so let's take a look. That graph looks like this. So we didn't know what the graph looked like, but that slope is actually negative 1 if you look on that graph there. So it is the correct derivative, even though all that stuff simplified and disappeared to negative 1. That is correct. Okay? So I'll give you another couple minutes to work out this one.
Yay,
Oh.
your favorite.
Need this one back? Okay, so I'll leave it here while you work, and then that third example we'll catch up together. Okay, so let's regroup here. For this piece, we were sort of talking about this in the class. E to the xy, it's your favorite derivative. It doesn't change, but there's a chain rule in here because there's a function. It's not just an e to the x. There's something else in there. So what I'm going to do is I'll leave it where it was, but I also have to multiply it by the derivative with respect to x of that xy piece. Okay? So you don't have to do it the way I did, but it's to remind you that there's an extra derivative to take. So I'll keep going here. This will be plus 2x, take away 2y dy dx equals to 0. Using the product rule for this piece, it will be e to the xy times 1y plus x dy dx plus 2x minus 2y. So this would be, if you got this far with it, that would be fantastic. It means the only thing that you could have made a mistake on from this point on would be your algebra. Okay? So what I'm going to do now is, as I said, I'm going to try to take all the dy dx pieces here and keep them on one side. So if I think ahead a little bit, there's one of the pieces together. So that'll be the piece x e to the xy times dy dx. That's these two pieces together. Okay. Then the other piece is take away 2y dy dx. And everybody else that wasn't involved looks like this. Here's the piece that has no dy dx.
You said it was dy dxy x dx.
Oh, that's not what he's talking. Yeah.
Okay, I'm gonna, you know what then? If that's, I won't shortcut. I'm gonna put it back up. I'm gonna just do it the long way, okay? So this would be, if I did it out the long way, would be y e to the xy plus x e to the xy dy dx. Okay. So there. I apologize if you didn't see both steps at the same time. But now my job was to...
That's not what I was asking about.
I'm going to have to get to your question after, Rick, because right now I'm in the middle of this one, okay? So right now I'm going to factor out my dy dx so that I can solve for it. So dy by dx, the pieces will be x e to the xy, take away 2y, and that will be equal to the pieces I don't have, which are here. So it would be take away 2x, take away y e to the xy. Okay, so now I can solve for that derivative. The derivative of y with respect to x is equal to negative 2x minus y e to the xy all over x e to the xy minus 2y. Okay, so that was a real messy one. That would probably be like level 5 out of 5 for us. But if you get the hang of the process, it won't get any worse than that. It'll never be that bad. So, if you could do 2 out of 3 of those confidently, hands up so I know how we're doing. 2 out of 3 confidently? Good.
It's a good day for math.
Good day for math, yeah. Okay. The next thing we're going to talk about, it's not any different from what you guys have already done. It's the higher derivatives, so we're going to look at a second derivative. But there's this one weird step that I'll admit, the first time I saw it, I had no idea to do it, but it'll make sense when I show you an example here, I think. So let me walk you through the first one. Okay, so this here is an implicit equation. Anybody know what the equation is? It's a circle, radius 5. Okay? Anyways, so if I take the derivative, it's going to be 2x plus 2y dy dx equals to 0. And now I'm going to rearrange this, so it's going to be 2y dy dx equals negative 2x, and the derivative of y with respect to x will then be negative x over a y. Okay. So that's derivative number 1. We're looking for derivative number 2. So if we want to find the second derivative, we have to take a derivative of the derivative. So yeah, it's going to be a quotient rule question. Let's take the second derivative and see what happens. So the derivative of the top piece is negative 1. The derivative of the bottom is dy by dx. And it's all over y squared. Now this is the thing that tends to mess people up is you have this extra derivative here, and you're kind of like, well, what do I do with this? Anybody have a bright idea? Yeah, this is that step. Oh, you got it?
Do you plug in the negative x over y?
Genius. Yeah, that's exactly what we're going to do. We've already figured it out here. So that's what we're going to just reuse that information. We'll put it in. It'll be negative y plus x times negative x over y. And I've got an improper fraction there, so I'm going to multiply to get rid of that fraction. So if I do that, I'll have negative y squared minus x squared over y cubed. Now, that is a perfect answer as far as I'm concerned. Your textbook, however, would do one more step. Does anybody see another genius step? You had your, yeah, you can take a break. You've had your genius step for the day. Does anybody see another step that might simplify it? Take out the y. How could we take out the y? I'm not sure that it's easy to do here. So, oh, you see something, James? Nope. Okay. I'm going to tell you and see if you can tell me why. Can anybody figure out why? Oh, a couple of light bulbs went on. Oh yeah, that's okay. So that's what it would look like in your textbook. And again, if you have to ask yourself, why would you do that?
Why would you do that?
Well, this is simpler. If you were looking for the third derivative, this is the version you'd want to work with.
Oh my goodness.
Okay? But you know, anyways, I'm going to let you try the second derivative. There's no extra tricks in the next one. You'll only have to make the standard replacement, okay? So try the next one here. Do the second derivative of the one I've got up on the board. All right, so it sounds like it's moving. I can hear a lot of good conversations. I'll try to catch up. So this will be negative 1 times y. Actually, you know what I'm going to do here just to make this?
But we need to do another one.
I know, but I'm just happy I got the first one.
Okay, what's the derivative?
I'm gonna take that with pride and just leave it there.
Yeah, just wait.
So I think if you were to take the derivative, you should, first derivative, you can check your work over against mine.
Okay, I'm not giving up the cheater mine.
And if I move everybody to one side and factor it out, I'm going to have negative x dy dx plus dy dx equals 1 plus y. So dy by dx is equal to, or sorry, let me factor it. And that'll be so I could write this as the derivative of y with respect to x is 1 plus y divided by negative x plus 1. And of course, you could write that as 1 minus x as well. It just so happened that's how my algebra turned out. So how many people got the first derivative of this okay? Okay. I'll give you just a minute then to take a look over it, and then we'll talk about the second derivative. If we're done the first one here, it's going to be a quotient rule that we're working on. So if I take the quotient rule, it'll be the derivative of the top, which is just going to be, so this piece here, it only has the derivative dy by dx. And the derivative of the bottom will be negative 1. So it'll be negative 1 times 1 plus y. And it'll be all over the bottom squared. So 1 minus x all squared. Okay, so now this was that part that I was talking about that it kind of seems like, what am I supposed to do with this here? And a lot of people get stuck thinking, how do I get rid of dy by dx? But remember, that's what we've already found right there. So when I put it back in, what I'm going to have is 1 plus y over 1 minus x. Okay, and you'll notice that it's kind of nice because these pieces will factor out. So I should end up with a 1 plus y plus 1 plus y all over 1 minus x squared. So if I collected up the like terms, I don't think we could do any better than this.
Oh yeah,
Okay.
that's all.
Okay, so
I like to make it.
so the last thing that I wanted to talk about with you in implicit differentiation is using the logs.
Yay.
Okay, now this is something that some of you missed this in the differentiation test, but when you come across a really terrible looking function, sort of like the one which is right here, this looks so awful that there's probably a little voice in your head should start saying, "Don't do it." And you should think about a better way of doing this. So some people, when they did their differentiation test, they actually tried to do this horrible, awful derivative, and I just, that would have been terrible. The idea was that you use the log laws to pull the derivative apart. Okay? We can actually go one step further and try and apply it here as well. So for example, if I have this, then if I was to log both sides,
Yeah, we can look at the size.
it could be any log you want, but the natural log is the most convenient because then I don't have to take, I don't have to change the bases around and stuff like that. So if I did this, we wouldn't have been able to work any further because now we'd be stuck. We didn't have implicit differentiation before. But let's go ahead and we'll use the log laws to split this up. I'll show you how much easier this derivative becomes to work with. So if I do this, I could split it into 2 times the natural log of x minus 2. And then I'd have to subtract 1/2 the natural log of x squared plus 1. Because the square root has a 1/2 exponent. Okay? So if I take the derivative of both sides of my equation, that means I'm going to have the derivative of the log is a reciprocal. So it'll be 1 over y. And I have to times it by the inside derivative. So that'll be dy by dx. Then what I have left over would be 2 over x minus 2. And this would be minus 1/2 1 over x squared plus 1 times 2x. Okay, so the pieces, if I wanted to solve this like we've been doing, and solve it for dy by dx, dy with respect to x is going to be y times 2 over x minus 2 minus x over x squared plus 1. Now, so far you probably agree with me that's a way, way better thing to do than all that quotient product and chain rule. But we have one more thing to do here. Originally, this was an explicit equation. We should not give an implicit equation. That's not the best form. But fortunately, it says this is what y is equal to. So I can take that piece and say y equals this. So why not put it back in? Okay, so in that situation, now I'm done. It's all in terms of x's. Look at how awful that derivative is. That's just terrible. But we were able to do it fairly easily to get to this stage by using the logs of both sides to take the derivative. Now, you have to use some caution here. One cautionary thing is that logs will only work when it's a positive number. In this example, it was specifically chosen because I have a square, which will be a positive number, and a square root, which only gives positive numbers. So positive divided by a positive means that function is always positive. So the log will have no problem working with it. Okay? So I'm just saying, don't make this your go-to technique for getting out of the chain rule and the product rule and the quotient rule, except for those times when it's obviously so terrible that the intention is you use this technique. Okay? So that's implicit differentiation. I'm going to give you guys some time now to work on your homework.